Let's solve now together two examples of logarithmic equations. We are going to see the examples and I want you to see the difference between the two. The first one has a plus, the second one has a minus. We are going to use the logarithmic properties in order to solve these equations. So we will start with A, and we have to be careful with what do we have in the equation. On the one side of the equation we have two logarithms, and on the other side we have a single logarithm. What we want in order to solve a logarithmic equation is to have a log of something equals to another log of something different. So single logs on left and right side of the equation. In order to manage to do that, we can use the property of addition, of multiplication for the logarithms that tells us that if I have two logs, the sum of two logs, then this is nothing else than the log of their product of the argument. So I have x here times x plus 1. And this is equal to the log of 12. Now, what I managed to do with applying the property of product is that I have now a single log on the left side and a single log on the right side. You can see that there are no bases here, so you can assume that this is the number 10. For the moment, we don't care about that. How do we solve this problem now? Well, if two logarithms are equal, then this means that the arguments of those logarithms will be equal. So this means that x times x plus 1 is equal to number 12. So immediately I can drop the logs. That's the beauty of applying here the properties. So what's the next step? Well, I have to observe here that I have no logarithms, no exponents, I have nothing strange, I just have a plain polynomial. So I need to write it as one of the known forms of my equations. If I distribute the x inside the parentheses here, I will get x squared plus x equals to 12. And if I move the 12 on the left side of the equation, then I have x squared plus x minus 12 equals to 0. And now I have a very well-known quadratic equation that I can solve using any method that I already know, either factoring or the quadratic formula. I'm going to do it with a quadratic formula only because I don't know if I have real solutions for this equation. So the quadratic formula tells me is negative b plus or minus square root of b squared minus 4ac. So remember your quadratic formula divided by 2a. Okay, in this case the b is 1, the c is negative 12, the a is 1. So I have an 1 here, I have an 1 here, that they are invisible, and I can plug in them in my quadratic formula. And what I have is negative 1 plus or minus square root of 1 minus 4 times 1 times negative 12 divided by 2 times 1. And this gives me negative 1 plus or minus. Minus times minus is going to be plus. 4 times 12 is 48. So I have square root of 49 here divided by 2. Square root of 49 is 7. So this gives me two solutions. The one is negative 1 plus 7 divided by 2. And the other is negative 1 minus 7 divided by 2. If I simplify, I have 6 over 2 is 3. And negative 1, negative 7 is equal to negative 8. So negative 8 divided by 2 is negative 4. Two possible solutions, and I say possibles because I'm not 100% yet that these are solutions. What do I need to do with x equals to 3 and x equals to negative 4? Well, I need to take each one of those and plug them in the initial logarithms, all the logarithms that I have in my initial equation, and see if I have any issues, if the x's, any of the x's, create logarithms that are not possible. So what I can see is that if I take the number -4 and I plug it in at the log of x, then I will have the log of -4. But there are no logs of negative numbers. So this means that this is not a possible solution. Then I take x equals to 3, I plug it in here and I have 3, log of 3, that is a perfectly legal logarithm. If I put the 3 here, I have log of 3 plus 1, that is log of 4. This is also a perfectly good logarithm. So the x equals to 3 falls in the domain of the logarithms right here, and this is an actual real solution for my logarithm. So always remember to check your logarithms, to check the numbers that you get out of your solutions, and ensure that one of them possibly will be a solution for an actual solution for the logarithmic equation. If you get two solutions, one of them for sure is going to be excluded. If it is possible that both of them will not work, you cannot be sure that one of them will work. Definitely one of them will not work. Let's solve now this equation, and it is a logarithmic equation again, but I have a minus right here, so this means that I have to use the quotient rule for logarithms. Remember, your goal is to have two logarithms, one on the left side and one on the right side. So if I apply the quotient rule, what I have is log with base 8, this doesn't change, of x plus 5 at the numerator divided by x minus 2 at the denominator is equal to 1. So what do we have here? We have two things. First of all, on the left side, I have a logarithm. On the right side, though, I don't have a logarithm, and I need to have a logarithm. So what do? I'm going to rewrite the equation. I will consider the base of my logarithm, the 8, and I will rewrite the right side with base 8 and argument 8. And as an exponent to the 8, I will use the constant that you have right here. So 1 is nothing else than log with base 8 of 8 to the first. This is what it says. So in this way, I replace the constant. It doesn't matter if it's 1, 5, 11, or 100. Whatever it is, you're going to take this base. You will create the logarithm with this base. Your argument will be the base. So this is how you get your argument for the logarithm. And the exponent will be your constant. And now on the left side, I keep the fraction as it is. And I have x minus 2 right here. And now that I have logs on both sides of the equation, and these logs have the same base, this means that since these two are equal, then this means that the arguments of those logs will be equal. So I can drop the logs. And what I end up having is x plus 5 divided by x minus 2 is equal to 8 to the first, that is 8. Now this is a much simpler equation that I can solve if I use cross multiplying. X plus 5. Remember one thing though, before you cross multiply, look at the denominator right here. This means that the x cannot be equal to 2. So this needs to be excluded from your solution. So if you solve the problem and you end up with x equals to 2, this is impossible. This is incorrect. So you have x plus 2 is equal to 8 times x minus 2 right here with cross multiplying. On the right side of the equation, the denominator is 1, since there is no denominator. I use cross multiply, so I have x plus 5 times 1 on the one side and x minus 2 times 8 on the right side. This is how I created that. And I continue with my solution, and I have to distribute now the 8 inside the parentheses. This is going to be equal to 8x minus 16. At the next step, I will separate the constants from the variables. My variable is x and 8x. My constant is 5 and negative 16. In order to do that, I will subtract 5 from both sides of the equation. This way I simplify the 5's. And then I will subtract 8x from both sides of the equation. In this way, I simplify the 8x from here. So I have now negative 7x equals to negative 21. I divide both sides with a coefficient of x. And this gives me x equals to 3. Okay, so that's now a candidate. It's a possible solution for my equation, but I'm not done yet. This is not necessarily the solution. The first thing that I need to do is to check with the x different than 2. And since x is 3, is different than 2, so I'm fine. The next step is that I need to go to the initial equation and I need to plug in the number 3 inside my logs. 3 plus 5 is equal to 8. Log of 8 with base 8 is 1, and this is good. And then I need to do the same for the second log. So I have 3 minus 2 is 1. Log of 8, log with base 8 of number 1 is also a perfectly good logarithm. So this means that x equals to 3 is an actual solution for this equation.